Oh, okay, so we'll start this one with this would be 6.2.2, right? We just finished 6.2.1, and this is about the first thing we're going to talk about is the Geiger-Müller tube. So think about what I just talked. In 6.2.1 we talked about the three particles that you're in radioactive decay that you want to be responsible for knowing about, which is the alpha, the beta, and the gamma particle. And each of these has the ability to ionize a gas as it rips through it, with the alpha being the greatest, and this one being the greatest, and then decreasing here in this direction to the right, with the gamma being the least. So remember the Geiger-Martin experiment that we talked about with the Rutherford gold foil under the direction of Rutherford? And Geiger also worked with Mueller, and they created a tube that detected these three particles. And so think about it, if these particles go through the air and they create ions as they rip through the air, let me just think about that. So here's the particle, and here's a oxygen with its protons and neutrons in the center, and then the electrons around here. So if it's going off in this direction and it hits an electron and rips it right off, an alpha particle, then the electron just goes off in some direction. Sort of like, almost, I guess you could just imagine it as like a collision, and that's exactly what's happening there. And it knocks off an electron. So thus, the oxygen then becomes a positive ion, and then you have a free electron moving around. So Geiger and Mueller looked at that, and they came up with a way of identifying these particles and as they're created. And so in the next slide and in your book, you'll see a picture of a Geiger-Müller tube, and here we have one as well. And so this part right here, I'm just going to mark up this. So this is a Geiger-Müller tube, and you have a charged anode here. I'm just highlighted it in red, and then the casing is another charged. It's a cathode. Now, anode and cathode can be positive or negative. It sort of depends upon the situation. So, but the important part is that they're charged, and so as the particles come in, and they come in, usually this is a mica. Mica is a mineral, a type of mineral, and you can make thin little sheets of it. And there's anthracite, and not anthracite, that's coal, sorry, muscovite and biotite, and are some types of mica. And so anyway, they make a little mica sheet there, and as the particle, remember, it can penetrate through this, so you could make it thicker if you wanted to just detect one type of radiation, or thinner if you wanted to detect all types of radiation. And so remember what I talked about with penetration power of the three particles. So as they go in and then they rip the electrons off of the gas in here, then that gas, now you have free electrons. So think about it, you got free electrons from the particles ripping through the gas, and then you have positive ions from the nucleus of the atom that you rip the electrons from. So they're going to attract to the respective sides, and when they do, here, as you can see, we've got a circuit set up with a potential difference across it. Right there's our potential difference, and then you start getting that's what creates the attraction between the two sides, and now you get a small current, and you can look at the current as a number, as a way of reading how many particles are being created, and then they actually put an audible reading on it as well, so you can actually hear when an ion is created and it hits. And I'll show you this in class. We have a nice Geiger counter, and we'll be able to look at this. And so that's a Geiger-Müller tube. Just what is the main emphasis of it? It's a tube that has a thin sheet that allows particles to come in, and as they come in, they ionize the gas inside of it. As they ionize the gas, that creates positive and negative ions in there, and then they are attracted to the respective anode or cathode, and then that creates a small current which can be measured. So going forward, the next thing that we want to talk about were Segre plots. Now Segre, and I'm you're gonna have to excuse me, but I don't remember his first name, but he was actually part of the. I'm pretty sure, I'll look it up to make sure, but was part of the Manhattan Project. And so he helped work on the nuclear bomb back in the 1940s in World War II. So remember so Segre looked at this and he saw there's about 2,500 nuclides. Now remember, that's a good definition one you're supposed to know. That's a atom with a specific number of protons and neutrons. And Segre thought, well, and if you just look at this, if you look at the periodic table, if you were to plot in your Segre plot, if you were to plot the proton number, I'll put proton number here, and versus the neutron number, and we'll just put a neutron number here, then if you look at the lower, like hydrogen, lithium, helium, and the lower number elements, you get a nice, just steady line increase like that. But as you go up that just means that as the proton number grows, the neutron number grows proportionally. But if you really start plotting all of the nuclides remember that's an atom with a specific number of protons and neutrons, then you start getting something like this. They actually, if you plot all 2,500, I guess, it ends up curving up away. So why is this? Why do you all of a sudden need more neutrons? Notice that as it goes this way, then that means that there's more neutrons than protons in the nucleus of an atom. So, let's think about why. Let's give a couple reasons why real quick here. So let's make a big blow up of an atom. So as you start adding more and more positive, then think about that these are going to repel each other. And so the likelihood that you get two protons becoming greater than the 10 to the minus 15th meters, which is the range of, I'm going to put strong nuclear force, okay, then these particles are going to become, remember that greater than 10 to the minus 15th meters, the strong nuclear force goes to zero. So, and then basically the Coulomb idea, or the electromagnetic force, that like charges repel, takes over, and boom, off you go. You got particles being ejected. And so that means that this is unstable. So in order to become more stable, in order to help add particles in there that still obey the strong nuclear force but are not subject to the positive push away, then if you were to add more neutrons, you can create a more stable atom. So that is what tends to happen as you get bigger. So you got positive particles in here, and I'm not going to be able to draw everything in here, and I'm just going to make, so those are positive particles, and neutrons will just be circles. So if you start adding neutrons in, a bunch of neutrons, more neutrons than protons, then you create a stable environment for the atom in general. And so there's still strong nuclear force interactions, but now you don't have that the interaction with the electromagnetic, where if they're both positive particles, they'll push away. Now it's interesting because if the atom gets too big, then remember what we know with beta decay, that a neutron decays into a proton plus an electron. So if the atom gets too big, it actually will make the nucleus unstable, and one of these neutrons will decay down into a proton electron to create it. And when you do that, you actually create a new element. So it's actually sort of converted over to a different element. Okay, so there's Segre plots, and wait, let's wrap this up with. So this is why, if you did proton neutron, you can add in that would be what the number would look like, but we know that it goes like this. And a lot of people I'm just plotting, I'm just making a mess here. But a lot of people like to call this the valley of stability. Because when you're in this area, which I'll highlight here, how about that? That's better. When you're in that area, you tend to have the right number of neutrons and protons in there to become a stable element. Okay, we'll stop on that one.